Okay, so that's started. Here's a textbook if you need it, and there's a outline if you need it. Just whiteboard and TV.
Whiteboard and TV. Okay. So the first thing we're gonna go over is the Pythagorean theorem. It's just a special rule that we use when we have right triangles. So right-hand triangle like this. So we had our triangle like this, A, B, and C. So basically it's a special rule which says that A squared plus B squared is equal to C squared. And this only applies when you have a right angled triangle, and we call the leg that is directly opposite of the 90-degree angle the hypotenuse. And depending on which angle you're looking at, there are special trig functions that we use called sine, cosine, and tangent. I don't know if you guys remember it from geometry. I remember they go over it very briefly. So we call this angle A. This one is part of it. Okay. Sine, cosine, and tangent are all just kind of special functions which are fractions. They're like a ratio of the legs or the lengths of each side. So SOHCAHTOA is how we remember each one. So in SOHCAHTOA, each letter represents kind of each of the functions. So goes with sine, ka goes with cosine, and toa goes with tangent. This just helps you remember which one of the legs you're going to use for each of the functions. So if we have this triangle, the opposite, which is O, would be the one that's directly across from the angle. So in this case, that'd be A. If we say A, we mean adjacent, and that's the one next to it, that's B. And then H is hypotenuse, which is this one, a really long one across the 90-degree angle. So SOHCAHTOA means opposite over hypotenuse. Or in our case, this would be A over C. And then for cosine, we have adjacent over hypotenuse, which would give us tangent is the only one which doesn't involve the hypotenuse. This one is opposite over adjacent, which would be okay. So these are our basic three functions that we're going to be using a lot in trig, and these are kind of what everything else is built off of. From here we can derive special rules that can help you guys solve equations and other things. So
question.
Yes.
So the opposite, like for opposite over the hypotenuse, is that in terms of like opposite angles or opposite sides?
So opposite just means if you take the angle, you just draw a straight line across, and you'd be looking at this one. So the thing about these triangles is that there's also another angle. So if I were to give you a triangle that looked like this, let's say it's the same thing as this one. So the angle A is here, B is here, and C is here. We can also use this angle B. So sine A is A over C, this is B over C, A over B. If we wanted to use angle B instead of angle A, and we wrote sine B is opposite, so the opposite of B would lead you to this one, and the hypotenuse still remains C because it's across from the 90 degree. So in this case, you have b over c. And then for cosine, your adjacent would be the other one. So right next to it, a over c. B opposite over adjacent. So when we do sine, cosine, and tangent, you kind of have to be careful about which angle they're pointing out to you, because based on the different angles, there'll be different ratios. And then, yeah, any questions so far-ish? Okay. Next, we're gonna go over cosecant, secant, and cotangent. So these are the reciprocals of our basic three. So cosecant, let's say theta equal to 1 over sine. An easy way to remember this is the co always goes with something that doesn't have a co in front of it. So cotangent goes with tangent. Cosecant goes with sine, because cosecant has a co but sine doesn't. And then secant doesn't have a co but cosine does. So just an easy way to remember them. And pretty much you're just taking these fractions and you're flipping them over. And they're just different trig functions that also come in handy. Any other questions? All good. Okay. So did you guys all bring your calculators? Okay. So on your calculator, there are sort of special ratios that we use for sine, cosine, and tangent. Does everyone know the 30, 60, 90 triangle? Yeah? Okay. Let's erase some of this. Okay. One, 3, 2. So you'll notice that this does follow Pythagorean's theorem. So 1 squared plus. Yeah. So let's say, so these three angles, well, 30 and 60 are some of the trig functions that we usually remember. And this is just because their fractions are pretty simple. If I took sine of 30, it would be 1 over 2. If I took sine of 60, it'd be 3 over 2. So these are just some basic ones that they usually test you on. These are things that you should have memorized. If you look at something and it says sine 30, you shouldn't even have to draw a triangle. These are just things that you should just kind of remember. And same goes for the cosines of these. Okay. Okay. That's pretty much it for sine, cosine, and tangent. And do you guys have any questions on these three trig functions? Oops, can you see, Kristen? Kind of, not really. Yeah. Here, stand on this side.
So you're just using the same rules that you put there, like just on that triangle, right?
Yep. The 30-60 triangle is something that they also like to test on in the SAT. They actually, at the very beginning, they had a little diagram at the front, which gives you these ratios, but you should probably memorize this one. It's useful for solving some of the triangles they'll give you later. You can derive formulas from this, like how to find the area of an equilateral triangle. It can be found from using this triangle and some of the rules they have. So neat stuff comes out of this. Okay, so we're gonna go on to angles of rotation. This one is not too hard. It's actually pretty self-explanatory. Okay. So if I give you like, if I tell you to draw, oh no, Lucille, your computer turned off.
Is this sleep or have battery?
I cannot tell.
Dang, what just happened?
That's okay. Okay, so let's pretend you're drawing a 30-degree angle.
Got it.
So usually you just think of this, yeah? And this is like 30 degrees. So these angles are kind of a special way to draw it. What we have is first you draw like your X and Y axis. So you have one side which is called the terminal side. And oops. And this side is the one that is always moving. So in this case, it's moving in this direction. Oh, golly. Wait, my bad. Oops. I think this is the initial. Okay. So your initial side is the one that you start with. It doesn't really move. Usually people use this keep this one as the x-axis on this side. So it'll be this one. The terminal side moves based on the angle that you're trying to draw. So if it's 30 degrees, you just kind of start from here and you gradually open it up until it reaches 30 degrees. So when we give you a positive angle, you automatically move counterclockwise. If I asked you to draw like a negative angle, you'd move in the opposite direction. You'd go clockwise. So if I said like draw negative 30 in standard position, you go this way and you move down. So eventually you reach something like this. Yeah, okay.
What do you mean by a standard?
So standard position is just you take an XY sort of coordinate graph, and let's say standard position would be one of the rays goes here, and the other one just goes wherever until it reaches the angle that it's asked you to draw. So let's say, for example, 120 degrees. Your first ray automatically goes here, then you open it up until you reach 120, which is roughly here. No, no more up.
Okay.
So this one would be called 120 degrees. So it's always the one here to here. Okay. So let's say they give you an angle that's more than 360 degrees. Let's say it's something like 400 degrees. Oh no, what to do then? So as always, you start with this, and you start with one on this side. So if you imagine like a clock, you go one round, and that gives you 360 degrees, yeah? So then you keep going until you reach 40 more degrees to reach 400. And that would give you this. So this is also considered 400 degrees. So something special about this is that sometimes you'll find that there are angles which, if you draw them in standard position, they'll give you exactly the same graph. So, for example, in this one, you'd say 60 degrees and 400 degrees are coterminal. So when you draw them, they're exactly the same thing. Wait a second. What is math? My bad. Yeah, that kind of makes more sense. Yeah. Okay. So
I don't understand why you drew a line for the 400 degrees.
yes. So essentially what you're doing is it's kind of like a clock, you know? Your minute hand can go like over and over in circles. And basically what you're doing is when you draw these lines, it's kind of showing your thought process. So you start from this line here automatically.
Wait, why do you start from that?
This one?
Yeah. Why don't you start from the x-axis?
Oh, this is the x-axis. I just kind of drew it hovering above it because otherwise it's kind of hard to
okay.
see. Yeah. So like if this is the starting line, you just go 360 and then 40 more.
Oh, okay.
Yeah. that would give you 400 degrees. So far, so good? All right. Okay, so now we're going to learn about reference angles. Reference angles are important for the sake of our trig functions. If I asked you to do, for example, sine of 150 degrees, that might be a little bit difficult because you don't know exactly what triangle to use. When I say sine of 30 degrees, however, you can go, oh, okay, I'll draw a triangle, or our little reference angle like this. This would be 30 degrees. And then you can use this triangle here, an imaginary little triangle, to find sine. But if I say 150 degrees, and it looks like this, one here, and one here, and you have this angle, then what triangle are you going to use? So basically, what a reference angle is it helps you find a triangle so that you can find these trig functions. So the way a reference angle works is everything always comes back to the x-axis. For 150 degrees, you look for the angle that will give you an acute angle, so something smaller than 90 in reference to this. So in this case, you'd use this angle right here. Another example. Let's say I do this. Oops. Okay, let's say we have 225 degrees. So does anyone have an idea of where the reference angle might be? Yeah. Okay, so since it's down here, we're looking for something close to the x-axis. So in this case, the x-axis that's closest to this would be the line right here. So our reference angle would be this one. Yeah?
Why didn't you have a reference angle?
So reference angles are important when using our trig functions. Trig functions are just ratios, right? So when you have something larger than, for example, 90 degrees, you can use a reference angle so that you can just use, so for this one, our reference angle for this 150 would be the 30 degrees right here. So we can say that like sine of 30, this could be a ratio that's like almost exactly identical to sine of 30. You just have to determine whether or not it's negative. So we have a little unit circle poster in the back, actually, that can help explain this.
You said radians yet?
No, I'm not going to touch the radians on there. So look at the points. You see what you take it?
You can just take it outside.
Okay.
You want it somewhere else? Or do you want me to put it?
No, I'm just going to hold it.
Actually, wait, I can put it on like right on the TV. Let's do that. You don't really need this screen.
No, not really. Not unless you're showing videos
Is
later.
this showing on the screen? Can you open that? Hang on.
Oh, I can't even find your mouse, which is not moving.
Whatever, it's fine. Don't worry about it.
Okay.
It'll be fine.
It'll be all good. Okay. So, oh golly. So the way we typically explain this is we take a circle. Which marker did I use? Okay. Okay, so as you remember, sine, cosine, and tangent are just ratios, right? So the easiest way to make a ratio for us is if we had something that was always 1, right? So the way we do this is we have a unit circle. Our unit circle is just a triangle, or a circle rather, with a radius of 1. So from here you can draw a ton of imaginary little triangles. For example, a 30-degree triangle, or a 30-degree would be this one right here. So to do that, we just look at our little circle. I'll draw an imaginary circle. Okay, let's draw a half circle then. Okay, so this is like our quarter circle from here, from the unit circle, and our radius is 1. So radius equals 1. And we wanted to draw 30 degrees. So, like you learned earlier from our standard position, if this is 30 degrees, so we can leave this here. The way to solve for this is we take an imaginary little triangle. So we draw from this point, and we draw directly down to form a right angle here. So this is 1, and this point is given. So let's call these imaginary points x and y. These would be our x and y coordinates, yeah? So the way to remember this is, rather, sine of this imaginary angle is opposite over hypotenuse, right? So if our hypotenuse is 1, since the radius is 1, this would be opposite over hypotenuse. So sine of theta is equal to y. This would be the y coordinate on our unit circle here. For cosine, we have adjacent over hypotenuse. So in this case, cosine would just be x. And then tangent would be opposite over adjacent. So the way we put this is we have a little circle, and we can draw different angles and then put the 3 different trig functions in terms of fractions for the coordinates. So the unit circle is just a way for you guys to use it and then find sine, cosine of different angles. So in this case, you guys remember that sine of 30 degrees is half, yeah? So we go to 30 degrees, which happens to be this one, and then sine is the y coordinate. So we go over here, we go to 30 degrees, and if we looked at the y coordinate going straight across, we'd find that it's half. So the unit circle is just a way, it's kind of a tool that people use to help them find sine and cosine of various different angles without having to memorize it. Yeah. Okay.
So can you, like, any triangle formed with a unit circle would have a radius of 1?
Yes. Basically, all you're saying with the unit circle is that any triangle that you've drawn, the hypotenuse is 1. This makes it really easy for us to find our various different trig functions. Since everything for sine and cosine is over the hypotenuse, and our hypotenuse is 1, basically you're saying that sine and cosine is just equal to the x or y coordinate. Right? Okay.
And what is theta?
Oh, theta is the Greek letter that we use to denote angles more often than not, rather than using x or y. Yeah. Interesting. Okay. Where am I going? Oh, I was on reference angles. Okay, why are reference angles important? So if sine is equal to y, there are certain points in our unit circle where y is negative. That's basically just below the x-axis, yeah? So every time we have a theta that's greater than 180 degrees, you'll notice that all the y coordinates are negative. So in this sense, anything that's 180 to 360 degrees, sine is negative for. If we apply the same thing for cosine, cosine is negative when x is negative. That makes cosine negative for all of these. So far, okay, making sense? Yeah? Okay, so why are reference angles important? Now that you have reference angles, you don't have to remember, oh, it's 210, it has to be, sine of it has to be negative half. Nope, you don't have to do that. So if you have reference angles, you can say 210. So this is 210 degrees. our reference angle would be just this one. So in this case, it would just be 210 minus 180, which would give us 30 degrees. So sine of 30 degrees, sorry, I'm just going to write this first. So we know that sine of 30 degrees is equal to 1/2. So let's draw an imaginary triangle. So the triangle that we've drawn kind of looks like this, with 30 degrees right here and our little right angle right here. So if you guys remember the special triangle from before, it looks like this. 3/2. Okay. So now that you've seen this, if we imagine this on our xy coordinate, x is negative, right? Since it's on this side. So we can say this is negative. And y is also negative, so we can say this is negative 1/2. And then this one will just be like that. So now that we have this, we can say sine of 210, which is this, can be just that, negative 1/2. So rather than remembering positive, negative, what's what, there's a handy dandy thing. Okay. This is an easy way to remember what's negative and what's positive where. The A, so the one that we use uses all students take calculus. You can change it based on whatever classes you like, something like that. So the A stands for all. This means that all of the trig functions are positive in this one. In this one, sine would be the only one that's positive. In this one, tangent is the only one that's positive. And in this quadrant, cosine is the only one that's positive. Yeah. So to understand why, you just have to kind of look at the x and y coordinates. So sine is positive here because y is still positive, right? So in this entire portion, sine is positive. Cosine is negative here because on this half of the xy coordinate, the x coordinates are negative. So that kind of explains why cosine is negative. Do you have a question?
No.
Okay. And then tangent is negative because if any one of these two are negative, then that automatically makes this ratio negative. So far, okay. In this one, both sine and cosine are negative since our x and y are both negative. Tangent is positive though because both x and y are negative. Since if you divide negative by negative, it gives you a positive. So that explains this one. Cosine is positive here since it's the only one of the three that has like a positive x coordinate. Okay. Lucille, can you kind of wake up? Oh, just kidding, I got it. Okay. Do you guys have any questions on the things that I've covered so far? Anything that I need to make clearer?
The SATC thing, are those like rules that you have to base the unit circle like rules on?
So these are just rules for sine, cosine, and tangent. If you'll notice, though, that the unit circle does follow those rules. So if we say that sine is equal to the y coordinate, you'll notice that if I took, for example, the second quadrant, it says that s, so sine is positive, right? If you look at all the y coordinates in the second quadrant, all of the y's are positive. So these two do align, just this is kind of like if you were to take a reference angle and you wanted to know, okay, which one's positive, which one's negative, this is pretty much something that you can use as like a handy little trick. Okay. So after this, we're going to be covering a different unit that we can use for angles. So far, we've been using degrees, like the little circly thing that kind of looks like Celsius or Fahrenheit, but we're going to introduce something else called radians. Okay. Whew, sorry, it's kind of warm. Okay, so 1 radian. If you have a circle, please do not mind my not very circular circle. And we said r is equal to 1. So if r is equal to 1, our circumference, let's say c, is equal to 2 pi, right? Okay. So the way a radian works is basically it's saying that in all of the angles over here, it can fit 2 pi of the radius. So it's just kind of a different angle that people use. On your calculators, there's a different function where you can change the sine or cosine to use degrees or radians. Sometimes that's how, if you're using your calculator for a question on a test or something like that, be wary of if the question has radians or degrees, because if you plug in a radians into your sine per se, when you mean to say degrees, it will give you a totally different answer and it will completely screw up your calculations. So how do you convert from degrees to radians? Okay, so let's say, so we know that an entire circle is 360 degrees, right? So now we want to put it in terms of this new radians. Since one radius is equal to 1, we can say that all of the angles in the circle are covered when it's equal to 2 pi, right? Because you've covered the entire perimeter of the circle. So we can say this is equal to 2 pi radians. Okay.
Why is it equal to pi?
So the logic behind this is that when you use a circle, you always want to say that the radius is equal to 1. It makes our ratios a little bit easier. So in order to cover the entirety of the circle or all of the angles in a circle, we need to cover the entire perimeter. In this case, our perimeter would be 2 pi, right? So we can say that 360 degrees, or the entire circle, is also equal to, for example, the entire perimeter.
So the circumference will be 2 pi then?
Yeah. Basically, 1 radian is like, if I were to take this in like a length of string, and I cut 2 pi worth of this length of string, and I laid it out around the circle, it would go around the entire circle completely. That's basically it. So 360 degrees is equal to 2 pi radians. From here, it's pretty easy to convert from degrees to radians or radians to degrees, but just for simplicity's sake, we'll just say so 1 radian is equal to 180 over pi degrees. So let's practice converting. We'll do the super simple ones first. So we'll do 0, 100, 90, 180, and 270 and 360. So for 90 degrees, let's say, and we wanted to convert it to radians, we would just multiply and say so we could say and then if we wanted to do 180, okay.
The left is like a different thing though, right?
Yeah. So this is for 90 degrees, and this is for 180. So if we imagine this on a triangle, it makes a little bit more sense. Let's say we have 90 degrees here. Like that. So if we wanted to find the circumference of a circle with like a quarter circle or 90 degrees, we could say, oh look, this is a quarter of a circle. So I just want to do 1/4 times 2 pi, and that'll give me the arc length of this, which is equal to pi over 2. Now, since this is also a right angle, it kind of makes sense. So our 90 degrees is equal to pi over 2. If I had half a circle, we'd say, oh, okay, it's 2 pi times 1/2, because it's like that. So then it would just give me pi. And so these just kind of using the conversion factors, but if you kind of think through it, the ratios here make sense. So for more complicated ones, for instance, 60 degrees, 30 degrees, just use this kind of conversion factor like you would for any other units. And on your calculator, there's a way to change from degrees to radians. On a scientific calculator, it's the DRG function or the DRG button. On yours, it's the... Lucille, do you know how to change from degrees to radians on this calculator? No? Okay, I have to do that before.
They aren't really using their graphing calculators very much.
Oh, okay.
Yet, so mostly just
It'll be important when you sign graphing later.
I know.
Okay, you can do it later
Yeah,
then.
we're dealing with graph calculators.
Okay. I think I'm pretty much done. Ish.
Okay. So why don't you guys take a 5 or 10 minute break,
Yeah.
and we will continue.
Yeah.
Straight down the hall. How do I stop this thing?
How do you stop it?
Oh, look, there it is.
Ha, ha.